Okay, so thanks everyone for showing up. It's great to see that the curiosity for how to use deep learning to solve PDEs is so big. Yes, so the program is as follows. I don't know when we start, but at least half an hour is a first part of the meetup. That's an incomplete literature overview of deep learning for solving PDEs. So that's, I would present 2 examples which have some nice features in them, I would say. And then we have like a 10-minute break for questions or anything. The second part of the talk will be more technical and also what we actually have been working with, because the first part is just literature, and I will not pretend to be an expert in everything I talk about in the first part, but I have some interesting things to say. In the second part, you can bombard me with more difficult questions, because I should be able to answer them, because I actually worked with it. And then you're welcome to stay for continuing discussion and some mingle if you like. So after this meetup, I hope that you have learned that deep learning is quite powerful to removing computational bottlenecks in algorithms. So you know that, or many of you know that from computer vision. Some of you also know that from dynamic programming or reinforcement learning. It doesn't scale classically, but with a deep learning approximation, it scales. And also that it's promising for solving PDEs and also for real-time nonlinear control. So the outline of the first part is that one slide about Syntronic and our algorithm focus here in Gothenburg, which is unique within Syntronic. Some high-level neural network preliminaries without much details. The first example will be generation of smoke in computer graphics. That's the Euler equation. And then something called physics-informed deep learning, solving low-dimensional PDEs using automatic differentiation in TensorFlow, very simply. And then PDEs in 100 space dimensions. In this first talk, I will not say anything technical. No, I will not mention an equation. But I'll just state some papers that will be useful for the second part. Okay, so Syntronic is a worldwide consultant company. So we have currently 1,075. We were awarded this prize, what's it called? Gazelle something. Yeah, Gazelle prize this year. When I started 2.5 years ago, we were 600. So I guess we deserve it, and we grow organically. We didn't buy any companies. We have head office in Gävle, and the main focus is embedded systems. But in Gothenburg, we have a focus on algorithms, and with algorithms we mean machine learning, sensor fusion, and automatic control. We usually included computer vision, but we didn't do so much computer vision, so I removed it. Some examples of things that we've done. When it comes to machine learning, we did quite cool things within master thesis. So more research-oriented machine learning was done in master thesis. In sensor fusion, we have a lot of customer projects, but yeah, we did some cool things in machine learning here in-house. And one was audio classification. So the first one was Swedish dialect classification with different exotic features and classifiers, and another one in real-time speaker recognition. We did some last fall reinforcement learning for production planning, which we will continue in the spring for reinforcement learning for warehouse scheduling. and we did some deep learning for stochastic control. That's what you will learn about today. Also some learning for connected home appliances, so some IoT. Sensor fusion, dynamic occupancy grids, automatic road segmentation, vehicle state estimation, automatic control, we're good at model predictive control, optimal path generation, some examples. Okay, so to some neural network preliminaries, I will not say anything about any of the biological analogies or so. This will, I see it from a mathematical perspective. So a neural network is a mathematical function with some special structure whose output-input relationship depends on some parameter vector. And here are two examples. So it has two inputs and one output. So it's a function from the plane to the real numbers. And if we add, if we have random weights, the graph of this function in the unit square looks like this. And if we add two hidden layers, the function is more complex, and you get a feeling for, if you actually train this, you can approximate quite nice functions, or complicated functions. So each individual parameter vector give a different function, and throughout this presentation I will write nn theta x for a neural network with some architecture, just emphasizing the parameter. And they are very powerful function approximators, and this can be stated or read from the universal approximation theorem, which says that in the unit cube in k dimension, any continuous bounded function can be arbitrarily well approximated with a neural network. And that's this kind of network with one hidden layer. The result doesn't say anything about how to, which activation function or how many nodes, or it's not constructive, it's just the existence result. But it says that this class of function is rich. And in this meetup, we'll use neural networks for approximating solutions to differential equations. And the goodness of fit will be in terms of error of the equation deviating from boundary conditions and the equation. There is no labels involved. One reason why this is important is that solving PDEs numerically with finite element, finite different, finite volume methods scales terribly. So it suffers under the curse of dimensionality, which in practice means that if you have an equation with more than 4 space dimensions, you cannot solve them at all. And 4 is extremely heavy, and also 3 is very heavy. Also on clusters. Yeah, I mentioned that before. Okay, so this is my first example from the literature. It's about generating smoke in computer graphics. And this is a picture from the paper. I didn't generate any of these pictures, but at least I cited it. So in order to do this, the Euler equation from fluid dynamics is used with some suitable boundary condition. And here the divergence here means the sum of the first derivatives in the respective coordinates. So here u is the velocity field of the fluid or the gas. So in every point in space and time, you have a vector point with a direction and a length corresponding to the velocity. And then you have a pressure field, which is scalar. And then for a suitable rho, which is density, force is F, and the domain omega, which is the geometry, for instance, the arch in the picture. Then this equation describes the physics for smoke well. So here's the rough sketch of the algorithm. So you initialize the vector field. It's a non-trivial task because both you want an interesting velocity field, but you also want it to be divergence free. So they use some wavelet method or something to generate this. I didn't study the details. And then for every frame in your animation, you do the following. You consider the equation without these two terms. This is an advection equation. That can be, or is in the paper, it's computed with a finite difference method, a suitable finite difference method. This is called a splitting scheme in numerical analysis. It says that you can do this first and then add the other terms. So you add the forces, and then you compute the pressure P with a convolutional neural network, which takes the numerical divergence of this field as input, as well as G, which codes the geometry of the domain, for instance, the arch. And then the final velocity field is computed this way. And this is visualized in the paper also. So you take the last frame, advect it, add the forces, compute the numerical divergence, scale with some number, use the convolutional neural network with the geometry, scale, redo the scaling. This would not, so a neural network is very nonlinear, but in fact this will be trained to do a linear projection onto a divergence-free vector field. So it should be linear where it is used. So therefore it works to scale and then rescale. Then you get the pressure field, and you compute the numerical gradient and you subtract. And this is the architecture of the network. So here is the velocity divergence, and then this is a binary occupancy grid. So it's a 1 if it's a rabbit in a cell, and it's 0 if it's just air.
So it's a kind of point space, or?
Yes, it's discretized. So the finite difference is discretizing the cube as a lattice with, say, 128 by 128 by 128. And in each such cube, you have a 1 or 0, depending on if you can have smoke there or not.
And it's the same for the calculation? You use the same small cells?
Yes, yeah. Both for the finite difference and for, as input to, so they use some high frequency filters here. They do max or average pooling in 2 different steps. So this sort of mid frequency information and low frequency information and high frequency information add this. I'm not 100% sure what they do here, but they get the pressure field. And I think the loss here is quite nice, because they do this a few time steps in order to get a stable projection. So the projection is the convolutional neural network. So they advect, project, a number of steps. And then they take the norm of the divergence squared. That's the loss function. So minimize it. And the weights, of course, the same weights come into every step here. So, and it seems to work. So I think the method is very nice, because it's no black box solution. It relies on physics and classical numerical methods, and it really removes a computational bottleneck. Because if you would not use the convolutional neural network, you would instead solve a Poisson equation in every time step, which is much more expensive than the advection step. So it removes that step. So to the second example, which is physics-informed deep learning. This is an example where they use it on the 2D Navier-Stokes equation. So here is some velocity or some fluid and some circular obstacle. And the vorticity is how much the vector field or the flow rotates. And the dynamics is quite complex, and it really captures it well. And it's from that paper. So there's 3 important papers, in my opinion. So the first one is what I would call white box PDE. It means that you know the PDE, you know all the constants and the coefficients in the PDE, and you just want to compute a solution. The second one, gray box PDE, you know the PDE, but there might be some constants. Not unknown functions in the paper, just constants. And then you use the measurement data together with your simulation to compute, to train both the solution to the PDE, but also the parameters of the equation itself. And then there's a black box PDE. So then you don't even know the PDE. So you train the network to find the PDE from data. So this is the type of PDE. So time derivative plus some differential operator, which has this form. So it's a function of the function and its derivatives up to order k. There's boundary conditions. So this is the boundary condition on the spatial boundary, and this is the initial condition. And approximating V with a neural network, the loss used is given on this form. These are called the collocation points. And in the collocation points on the boundary, we want the neural network to satisfy the boundary condition. And in the collocation point in the interior of omega, we want the equation to be satisfied. And this is just moving this term to the other side, and it should be 0. And to do this, automatic differentiation is used. And so it relies on the fact that the neural network, or most function, is a composition of elementary functions described by nodes in this computational graph that TensorFlow uses. And then using the chain rule and derivatives can be generated quickly using the graph and the derivatives of the individual nodes in the graph. And this is extremely simple code-wise in TensorFlow. So if V is just some neural network defined somewhere, and we concatenate the time and x, and then you can just take the time gradient and the x gradient, then we have vt and vx, and vxx is just the gradient of vx and so on. So it's extremely simple. And an equation from the paper is the Burger's equation, which looks like this. There's application from fluid dynamics, nonlinear acoustics, gas dynamics, and traffic flow. And again, in TensorFlow, this is ridiculously easy. So the loss is just everything in the equation moved to one side, power squared. And then of course you have to do perhaps some batch, or you have to take into account the collocation points and so on. So it's not fully true, but essentially. This is the result or actually they take 100 collocation points on the boundary. It's these points, a lot on the initial boundary and more sparse on the spatial boundary. This is where the equation starts, and it evolves in time until the final time 1. And here they plot the solution for one time point. The exact one is the blue, and the predicted one is the red. And on this scale, it's impossible to see different. There is an error, of course, but I'm not going into that kind of details in this talk. So I think also this approach is very appealing since it's extremely simple. And TensorFlow is extremely powerful a tool. A drawback is that no equation they consider have more than 2 space dimensions. And it's any PDE with a lot of, it will not scale to higher dimensions. It will suffer under the curse of dimensionality. Every method that uses a fixed number of collocation points. And one way you can think about this and understand the curse of dimensionality is that, say in 100 dimension space, the cube, the unit cube or any cube in that number of dimensions have this number of corners. And using only the corners as collocation points, that would be a terrible idea. So you would need much more collocation points than this large number. So that gives a feeling of the curse of dimensionality. Okay, so my third example, which essentially will be presented in the second part of the talk, is based on this paper. So they solved PDEs in 100 space dimensions using backward stochastic differential equations. So this is paper for semi-linear equation. Yeah, this is nonlinear equations. And there's also a recent development for extending this with some automatic differentiation. There's no really good comparison between the result or the method, so I cannot say if that's good or not. Okay, so they solve several equations in 100 space dimensions. So heat equation, some Hamilton-Jacobi-Bellman equations. But the most relevant examples are from stochastic or from mathematical finance. For instance, if you would price an option based on, say, 100 underlying indices, the stocks, then this could be used. And in the second part of the talk, I will exemplify and explain this method on the Hamilton-Jacobi-Bellman PDE for inverted pendulums. And that's time for a break. Okay, so in the second part of the talk, this is the outline. I will show you some animation of inverted pendulums. And then I will introduce you to stochastic control theory, deep learning regulators, which are based on the stochastic control theory, and control of inverted pendulums of this type. So there's a cart which is moving without friction, and there's a joint here without friction in the simulations, and the pendulum is free to swing, and we want to control the force U to make the pendulum stand upright, and we usually want to start from a downward position. And in order for you to appreciate the animation, it's good to know that the classical methods for this splits the control problem into two. So first you let the pendulum come into equilibrium, and then you have a pre-recorded control signal that sort of swings up the pendulum close to the unstable equilibrium point, and there a linearized differential equation is used, and a very cheap regulators like the linear quadratic regulator can be used. That's the way to do it, but then you have to wait until it's in equilibrium. But here we can start with any initial value because we use the nonlinear dynamics for the whole problem. And since it's a very small neural networks that generates the control, we can do this in real time. Yes, and I will show you the animations first because some of you will get lost here, I'm sure, because this will be the most technical part, but I think it's important. But at least you know where we will end, and also here you will be able to rest your eyes on some plots, and it will be more soft again. But these are 11 slides with some more technical material. Okay, so the first animation is two pendulums starting in the same downwards, but with different angular velocities, and they will, yeah, you will see. It's quite nice. So it's done with this, with the deep learning regulator. And then there's two movies or animations of double inverted pendulums with two different initial values, you will see. Difficult to do that by hand. Yeah, so that's. Yeah.
But you stop it exactly when it's like solved. But is it? I mean, isn't there like a little bit? Because it's not exact, right? Like the solution.
No, it's not.
So would it have to regulate itself
more? You will see other examples later. You can have there's a terminal cost function and there's a running cost function. And depending if you have a large running cost or terminal cost, you can change the behavior of the regulator. I think this is mainly a terminal value. So you only want it to be still at a certain time, which is half a second here.
Do you have any robustness there in case your actuators cannot achieve exactly what you calculated?
So this is based on stochastic control theory, which we add some Gaussian noise to the model. So it's a stochastic differential equation, and which makes the regulator trained in a larger region because the dynamic is, say, evolving more erratically. Even we add quite small noise, so it looks physical. But I think if you would say push the pendulum and add some impulse to it, it will fix it if it's small enough. But if you would do a completely deterministic control, you would lose robustness. Yeah. Okay, so in stochastic control theory, we have a state equation. If we remove a W dot here, you have an OD that most of us studied in the first year of engineering. If we add this, then there's some Gaussian noise added to it, and it's a stochastic differential equation. And the stochastic differential equation is controlled by some function or stochastic process u, and how well the control is doing is measured in terms of this cost functional, which is the expected value of some running cost, which is accumulated over the time that we control, and the terminal cost. And for those of you who know stochastic analysis, this should be interpreted as an Ito ST. So how many here studied a course in stochastic analysis? A few, so that's good. Yes, and the stochastic control problem reads that we want to minimize the cost for some control in some space of stochastic processes. No details there. So in the part of stochastic control theory known as dynamic programming, the value function is important. So under certain assumptions on the coefficient of the equation, the running cost and the terminal cost, it satisfies the dynamic programming equation, which is a second order PDE with this a bit odd looking infimum in it. Why is it good? Because the optimal control is given as the minimizer of this. So if we have the gradient, then we're in a very good shape of doing very good nonlinear control. Optimal in terms of this cost function. Yeah, so depending on assumptions, there exists a so-called optimal feedback control, which means that the optimal control is a deterministic function of time and state. If we know it, we know how to control optimally. And from this expression, these are known. If we would know the gradient, we would have a function, the function we have anyway, of this form. So it's a function nu of x and the gradient. That's the form of the feedback control. And deriving nu in concrete examples, for instance the one for the inverted pendulums, is an easy part of the problem. I mean, it will take, it's a bit cumbersome, it's some algebra just to derive it. But it's not a difficult part of the problem. But the problem is that computing the gradient is a non-trivial task. Okay, so one step further to being useful is the Hamilton-Jacobi-Bellman equation. That's essentially the dynamic programming equation, but with the optimal v inserted, and we know the optimal v has that form. So if we define the nonlinearity with nu in it, to introduce some new notation, then the dynamic programming equation transforms into the Hamilton-Jacobi-Bellman equation, which does not have the infimum. It's just have different functions here. But there's a problem. So classical numerical methods for PDE suffers under the curse of dimensionality. So I would not recommend anyone to do finite difference or finite elements or something for that, for control problems. That would be completely academic and not interesting. So one step further to actually being useful is that we formulate this in terms of a forward-backward stochastic differential equation. And doing that, we do that by defining a stochastic process y, which is just the value, that's the optimal cost, at time t evaluated in the state, and the same for a process z, which is the gradient of v. And then the most important theorem in stochastic analysis is known as Ito's formula, and combining it with a Hamilton-Jacobi-Bellman equation, x, y, z satisfies this equation. It's a forward SD because it has a forward initial value, but it's coupled to something which is a backward stochastic differential equation, which is because it has a terminal condition. Problem. So classical numerical methods for FBSD suffer under the curse of dimensionality, possibly even worse than the PDEs. But we're still approaching something useful. And the solution is that do a neural network approximation of the gradient trained to satisfy the terminal condition. And in this network, the equation is built into the architecture of the network. I will explain that. I will use 3 different regulators. The deep naive solver regulator, that's from available in the literature, 2016. And a deep FBSD solver regulator and a deep E regulator. That was introduced by our master thesis student, Christopher Andersson, who submitted his thesis for print last week. It's a very good work, I would say. We supervised it during the spring and until now. And this was based on this paper from 2017 on a deep learning based numerical method where they computed solutions to 100-dimensional PDEs. So the approach is based on discretizing the forward-backward stochastic differential equation with the forward Euler scheme. And this reads, so for arbitrary z0 to zn minus 1, the scheme reads as follows. So we have no method to generate this, so they have to be arbitrary from the beginning. Initialize x and y. The noise increments are Gaussian, just sampled, and this is just forward Euler time stepping for a stochastic differential equation. But there's problems. The y0 is part of the solution and is not known a priori. So doing this doesn't make sense. z0 to zn are completely arbitrary, so they're absolutely not a part of our solution. That doesn't make sense. And the terminal condition is not respected. So this does not give an approximation of the solution. So the solution is, because we can look at here, we know that y is a function of x, and we know that z is a function of x. So if we make an ansatz with neural networks and train them in the right way, we can actually do something good. And that's what we do. So we consider a big neural network with the initial values and the noise increments as the input, and the terminal conditions of x and y as the output. And the computational graph for the network is built in the following way. So x0 is just the initial value, y0 is the neural network, one neural network of x, and then for every time step, z is a function neural network of x, and this is just the Euler time stepping. And the neural networks are fully connected, very small networks.
X, Y, and Z.
It's the solution to this forward-backward stochastic differential equation.
Is it from pendulum still, or
This is general.
general?
Then we will apply it to the pendulum. And in the case of the pendulum, not mu without the tilde will be the dynamics for the differential equation for the motion model for the pendulum.
And X and Y?
I beg pardon?
For the pendulum, what will be x and y?
X will be the real physical state, and y will be the value along the trajectory. Given that you're in X, this is the optimal cost that you will get if you continue to control in an optimal way until the last time. Good question. Let's see. Yeah. So the noise increments are Gaussian. And we also want, as I said, we wanted the pendulums to be able to have different initial angular velocities and different positions and so on, so that we can sample the initial value uniformly in some domain where we want to use the regulator in. So it's a quite nice network. We know we don't have any, as I said before, we don't have any data, but we have an exact distribution that we can sample from and make single batch stochastic gradient descent updates from that. And the loss function is just punishing y deviating from g of xn. So it's a mean square error. And this is approximated with Monte Carlo with one sample. That's what it means with single batch. And when the networks, so we had the big network. This was only a help. It helped us to train something sensible. But it's these networks, not that, but these networks that are useful because they approximate the gradient of V. Let's see. And when they are trained, we get the optimal or approximate control this way. The second controller is easier. It relies on some sophisticated control theory. It relies on the dynamic programming equation, the fact that we knew this function nu. That is used, but otherwise no forward, backward SDs and so on. But still we use some more structure of the problem, which we will not do in the last one, which is called the naive one. So here we generate essentially, that's the naive. Here we generate, say, the gradient of V. And we know that from this expression, we get the optimal control via mu tilde. And instead of trying to make these forward and backward equations satisfy the terminal condition, we just hit the cost functional directly, discretize it. So this is like a Riemann integral, numerical integral. So we want to find this function which generates the best control in terms of the cost functional. And then we have the naive. Then we don't use the function nu. So we don't use any structure of the problem at all. We just look at the problem. We have a cost functional and just simply generate the optimal control in terms of x. So it needs an assumption that the control is of feedback form, but else than that, it's nothing sophisticated. And just updating it. And minimizing the cost functional. Yes, and it's available in the literature. Okay, so now you can rest your eyes on some plots. It will not be that technical anymore. The state for the single inverted pendulum is position velocity, angular velocity, so it's a 4-dimensional state. So also the PDE is 4-dimensional, which makes it also a difficult problem. We add some noise to it. You will see on the plots why I think it's good to add noise on it. Yeah, the double inverted pendulums, then we have 2 angles and 2 angular velocities. We're in 6 dimensions. And we use the most classical cost function in control, automatic control. We use the quadratic one. So R and G are just 4x4 diagonal matrices for the single inverted pendulum and 6x6 for the double. We use unbounded control, so that's a natural, if we would do another master thesis, it's a natural direction to consider constrained control, constraining both the control and the state and so on. The subnetworks are, we use 2 hidden layers with a really low activation function and 4 hidden 14 nodes in each layer for the single inverted pendulum and 26 for the double. So it's very small networks. And 100 time steps are used. The terminal times are 4 seconds and half a second for the single and double inverted pendulum. We had problems with numerical problems with the double inverted pendulums because it happened since it's a discretization and there's noise added to it. It could be that the pendulum would go like that, but due to numerical errors, it goes the other way, and that screws up the numerics and the training. So if we stack these small networks on each other, like we do in this loop, then we have 303 trainable hidden layers. And if you allow me to define an Euler layer, which is just update with the Euler method, then it's 100 extra Euler layers. So it's a very deep network to train, but in the end we only use the subnetworks, which are very small. And this is the cost during training. So it's not the loss. It's the loss for the... so the green one is the naive solver, and the blue one is the forward-backward stochastic differential equation solver, and the orange one is the DPE solver. For the DPE and the naive solver, the loss and the cost is the same, but for the other one, it's different. And this is the cost. So how good is it? How does it improve during training with, say, 10,000 iterations? And they are quite comparable. But the naive solver or regulator, it's worse. It lies above. And the other two, it's impossible to distinguish if one is better than the other. And these are 2 different cases. So here we have low running cost. So we punish the behavior or deviation from the desired state at the terminal time. In the second one, we have a high running cost and low terminal cost, or actually no terminal cost at all. So we only care how it behaves from 0 to t. And for that one, the naive solver is much worse. And the other 2 are again comparable and seem to reach some level, very stable level. We don't have any method to show that it's close to the real optimal control, but yeah, at least the behavior in the graph is quite nice. Yes. And these are plots from 500 simulations, and then we removed the 2.5% highest and the 2.5% lowest values to get the 95% empirical confidence interval. And the vertical position ends up close to 0. The vertical velocity ends up close to 0. The angle pointing down close to pi. is stabilizing to 0, and the angular velocity is also close to 0. Here we use a larger domain of initial values, so we let we take initial values between 2 and -4. And I think that is also good, because you see that this is the area where the trajectories have been, which it means that that's where the controller is trained. So that's about the robustness. If you would go here and you would give it an impulse or disturb it so that it ends up here, then it will be trained there. But if you give it a very big impulse so that it ends up somewhere up here, then it will absolutely fail to extrapolate and generate a sensible control up there. So having big initial values and also adding the noise so that these areas are fatter gives a more robust control. This is the one with large running cost and no terminal cost. So it's quite clear that it stabilizes earlier, and then it's stable. It's at a quite early stage. It is almost at the equilibrium, but it seems like the cost for punishing the vertical position is very low. So it's going very, very, very slowly towards 0. So it's at -7 here. But that could be fixed by just adding a larger weight or penalty term for the vertical position. This is the cost plot for the double inverted pendulum. There's 2 different cases here. It's the essential difference is the low noise level. And they also have different initial values, and that was the one you saw on the animations. So this was pointing down, and one was pointing down, and the other one was pointing upwards. So the first one with the low noise, the naive controller is not impressing. The other 2 are comparable, but it would be more satisfactory to continue this until it is stabilized completely. But these plots took a lot of time to generate. So I guess we'll write a paper about this, and then we will have plots which are fully satisfactory. And the second, when we add the noise level, we get for the first time a benefit for the FBSD regulator. So it's really better. And even the naive seems to be better than the DP. So we have a reason to do the difficult things. That's a good result, I think. But we tried also very simple toy problems in 1 dimensions, and for them the naive solver was always the best one. So it depends on the problem, which one to choose, I guess. And these are the angles seems to do what it should, and the angular velocities also, and they are quite fat, so I guess they correspond to the high noise dynamics. So I think the conclusion is that the method works quite fine, and the main benefit is that it works for a large range of initial values, and it can be generated in real time, because nonlinear control is a difficult field, and usually you do various kind of linearizations, and it's a horrible mess to really understand the algorithms, and it's a research field. So I think this is an opportunity to do something much simpler, and actually you don't need to linearize. You can do the fully nonlinear problem without any problem. Of course, if you do another problem, then you have to verify that, but for this problem it worked. Yeah, so thanks for your attention. Any questions?